Electricity, a mysterious and somewhat spooky force of nature. It long remained unexplored. Not until the start of the 17th century did scientists begin to investigate it systematically, in the hope, perhaps, of exploiting it. One of these researchers made the breakthrough, the Englishman Michael Faraday. In 1821, he built the first prototype electric motor, and 10 years later, the first prototype generator. In 1600, the English doctor and physicist William Gilbert published his work De Magnete. Using the mineral magnetite and a needle, he demonstrated the effect of magnetism. Gilbert was also the first to distinguish between magnetic and electrical phenomena. In 1767, another Englishman, Joseph Priestley, built his electrical machine, in which friction produced electric sparks. Priestley had some intimation of the importance of the mysterious force. In electricity, he wrote, one can place the strongest hope of new discoveries. There was another discovery too, namely that the more sensational aspects of electricity could be a money spinner. Travelling showmen demonstrated the strange effects of electric currents, mysterious crackling, bright sparks, and, the climax of the show, a knife point that could ignite alcohol. Contemporary scientists remained aloof from these popular displays. They were more interested in the causes than in the spectacular effects. In 1789, Luigi Galvani, the professor of anatomy at Bologna in Italy, carried out experiments with frogs' legs. If he touched the nerve fibers with two different metals, the muscles suddenly twitched. Galvani was convinced he was getting the frog's leg to demonstrate its animal electricity. He was wrong. Not long after, another Italian, the physicist Alessandro Volta, showed that two different metals were enough. You didn't need any animal parts. The effect could be greatly enhanced by putting acid between the two metal plates. On this basis, Volta developed the first battery. The voltaic pile was the first device to produce a continuous electric current. It was a decisive step in electrical research. The Englishman, Sir Humphry Davy, was interested in the decomposition of materials by electrical means, a process known as electrolysis. At the Royal Institution in London, he demonstrated how a voltaic pile could be used to break down water into hydrogen and oxygen. A young member of the audience followed the famous chemist's lectures with particular attention. His name was Michael Faraday. A bookbinder by trade, he took careful notes and added sketches of his own. A few months later, Faraday sent Davy a bound edition of his collected notes and asked if he could be employed as his laboratory assistant. Davy was impressed and said yes. It was the start of an extraordinary career. Michael Faraday was born on the 22nd of September 1791 in the village of Newington near London, the son of the local blacksmith. 5 years later, the family moved to the capital, but when his father became ill, they fell on hard times. Young Michael learnt to read and write at school, but little else. After helping to feed the family by running errands, he was apprenticed to a bookbinder at the age of 13. Thirsty for knowledge, here at least he had access to books. He discovered a volume of the Encyclopaedia Britannica with articles about electricity. Fascinated, Faraday began to build apparatus of his own. His interest had been fired. During his first year as Davy's assistant, Faraday acted as his secretary and manservant when his master went on a grand tour of Europe. The journey took them to Paris, Florence, Rome and Naples. Faraday met everyone who was anyone in European science. In the next few years, Faraday advanced to become a scientific assistant at the Royal Institution and began to give lectures of his own. Like many scientists of his day, he was fascinated by an experiment performed by the Danish physicist Hans Christian Ørsted. In 1819, Ørsted had shown that a compass needle was deflected by an electric current. It was the first piece of evidence that there was a connection between electricity and magnetism. Faraday replicated Ørsted's experiments, but then he changed the setup by hanging a small piece of wire over a bar magnet. Then he connected it to a source of electricity. Not only did current flow through the wire, but the wire started continuously revolving around the magnet. What Faraday had done was to generate a mechanical magnetic force by means of electricity, a force which caused the wire to rotate. In so doing, he had discovered the principle of the electric motor, an epoch-making discovery. But Faraday was not content with this. He wanted to know if the effect could be reversed. Could the magnet be used to generate electricity? He connected a voltaic battery to the ends of a wire coiled around an iron ring. A second wire, completely insulated from the first, was likewise coiled around the ring. He attached the ends of this wire to a galvanometer, a device that detects electric currents. When the current started to flow in the first coil, a magnetic field built up around the iron ring. As a result, a short surge of current was triggered in the second coil, causing the magnetic needle in the galvanometer to deflect. But although the current continued to flow in the first coil, the galvanometer registered no more current in the second. But when Faraday interrupted the current, the needle deflected once more, albeit in the opposite direction. In this experiment, Michael Faraday had succeeded in transferring electrical energy. But why was there no continuous flow of current in the second coil? After all, the magnetic field was constant. Why did he only get a surge of current each time he turned the apparatus on and off? Faraday tried to find an explanation. He was helped by his talent of drawing the right conclusions from careful observation and visualization. When he scattered iron filings on a magnet, he noticed that they formed a regular pattern. The pattern displays lines along which the filings arrange themselves. Faraday called them lines of force and discovered that they filled the entire space around the magnet. Later, Faraday was to coin the term magnetic field, which has been used ever since. He came to the conclusion that an electric current in one wire can only be transferred to another at the moment when lines of magnetic force cut across it. So, if a current begins to flow in the first coil, lines of force form and cut across the second coil. In so doing, they induce a brief surge of current in this wire. But as soon as the current in the first coil has reached maximum strength, the lines of force stop moving. The current in the second coil ceases to flow. If the circuit is interrupted, the lines of force shrink back and cut across the second wire once more, but this time in the opposite direction. The result is another brief surge of current, also in the opposite direction. Faraday was now convinced that when lines of force pass across an electrical conductor, they trigger a one-off electric current in it. He called this effect electromagnetic induction. Then he asked himself how the process might be made continuous and not just brief one-off surges. In 1831 he solved the problem with a simple but brilliant idea. He set up a copper disc so that part of it was between the poles of a horseshoe magnet. Then he set the disc spinning. It constitutes a moving electrical conductor between the poles and thus keeps cutting across the magnetic lines of force. In this way, a permanent current is induced in the copper disc. Faraday had invented the first generator, probably the single most important invention in electrical engineering. News of his experiments on electromagnetic induction, which he performed in his lab at the Royal Institution, spread like wildfire. The one-time lab assistant had become a world-famous scientist. In 1833, he was appointed Professor of Chemistry at the Royal Institution. But for all his success in the field of electricity, Faraday saw himself first and foremost as a natural philosopher. A versatile man, he investigated the influence of light on plant growth, analyzed meteoric rocks and the northern lights, and he continued to feel at home in chemistry. He discovered benzene and liquefied gases such as chlorine and ammonia. One of his discoveries is still associated with his name. In 1836, Faraday discovered that a metal cage only conducts electricity on the outside. Inside the cage, the strength of the electric field is zero. This insight should reassure all motorists caught in a thunderstorm, because a car is in effect a Faraday cage. The occupants are safe even if the car is struck by lightning. But Faraday's most important invention was and is the generator. Instead of weak and expensive batteries, the generator opened up the possibility of large-scale cheap power. Even today, all electricity produced by generators goes back to the principle of electromagnetic induction, discovered by Faraday. In a hydroelectric power station, for example, water drives a turbine, which in turn moves a coil in a magnetic field, and out comes electricity. It is a surprising and extraordinary fact that Michael Faraday derived all his insights from creative experiments, precise observations, and an understanding of how nature worked. He conducted tens of thousands of experiments and never published a single equation. This task was taken on by the Scottish physicist James Clerk Maxwell, who converted Faraday's 60 years of experimental results into mathematical form. These equations and Faraday's discoveries are still regarded as the high points of 19th century physics. Michael Faraday died in his house in London on the 25th of August 1867 at the age of 75. He understood, like few other scientists, how to translate fundamental experiments into practical applications. Even today, on the east coast of England, there is a lighthouse designed by Faraday as a prototype. It is still working. It is a memorial to a man who, throughout his life, united practical genius and an unquenchable thirst for knowledge.